Okay, guys, follow up on categorical analysis, more specifically chi-square, and we. I want to take a look at a couple things, and I'm going to create a new problem for you, and just run through it with you. Uh, Remember the problem we had before that looked at the relationship between political party and beliefs about abortion, pro-life or pro-choice. And what I've done up here in the circle, I've just given the model or the expected values. Uh, One thing we did last time in the previous videos, we did standardized residuals. And remember that the standardized residual was the observed value for the particular case minus the model for the particular case over the square root of the model or the expected value. I think we calculated one of these, but I don't think I got into the interpretation. So let's just focus on the calculation and interpretation for the standardized residual for pro-life and being a Democrat. So guys, clearly the observed is 150. The model gives us 250. And I think I did this actually in the previous video, but I don't remember exactly. And so let's get our calculator. And we get negative 6.32. Now, what does this tell us? Again, I kind of look at the threshold of negative 1.96 to positive 1.96, and this clearly falls below negative 1.96, so it would be of interest to me. And it turns out in this situation, all the cells are of interest. But this tells us that the observed cell count for Democrats who are pro-life is 6.32 standard errors below the expected cell count. So guys, under the null hypothesis, which says that there's no relationship between political party and beliefs about abortion, what we get in this particular cell count right here turns out to be 6.32 standard errors below what we would expect to get under the null hypothesis, where there's no relationship between a political party and beliefs about abortion. So this number seems quite high based on the null hypothesis. Now, let's get into everybody's favorite. Can't even say it without laughing. Effect size. All right, so looking at effect sizes for and let's just review. What should we know about effect sizes? First of all, I think they're very confusing. They're really extremely confusing to calculate and know which one to use. That's why I always just keep handy a really reliable resource. But effect sizes just give us at the end of the day kind of a significance value of a study. Where we can compare results from one study to the other. We typically categorize effect sizes as small, moderate, or large. Luckily for us, we really don't calculate an effect size for categorical analyses. It turns out that the odds ratio which I presented to you guys way back when in Math 5500 when we were looking at logistic regression. Uh, I don't guess you knew that odds ratio were really effect sizes, and you shouldn't have. But it turns out that they are. These are actually most appropriate for 2x2 designs. What I'll probably do in a later video is show you how I feel that these things can be manipulated. Is say you've got a 3x3 or 3x4, what a 2x3, whatever it may be, how we can actually use this concept, if you will, to make meaningful determinations on effect size, even if we have a design that's not a 2x2. And the cool thing about these, unlike many effect sizes, these things are really, really easy to calculate. So, guys, let's stop all the all the talking and let's get down to how we calculate these things. First thing I'd want to do is I would want to look at, for example, the odds of being a Democrat and pro-life. And the way we calculate this is we just look at the number or the frequency or the count of Democrats or pro-life over the number of Democrats who are not pro-life. All right? So, in our counts, we have 150 Democrats who are pro-life, and being not pro-life is the same thing as being pro-choice. So that's going to be 400. So guys, we have 150 divided by 400, and this comes out to be 0.375. Now this is not an odds ratio yet. This is just an odds. And again, you know, kind of the end goal here is to come up with what we call an odds ratio. Next thing I'd want you to look at is I'd want you to think about the odds of the other column. And the other column is being a Republican and pro-life. So guys, just as before, the odds of being a Republican and being pro-life would be the count of the Republicans who are pro-life divided by the count of the Republicans who aren't pro-life and 250 divided by 80, it's 8.33, no, 3.125. Now, what we want to do now, we've got this, we want to come in and do the odds ratio. And we want to do the odds ratio of the odds of being a Democrat and a pro-life to the odds of being a Republican and pro-life. So I'm going to have 0.375 here. And I'm going to have 3.125 right here. Clear enough? So guys, we have 0.375 divided by 3.125, and we get 0.12. Now, this is our effect size, and at the end of the day, what this tells us is that the odds of being a Democrat and being pro-life is 0.12, being a Republican and pro-life. Now, I don't know about you, but to me, when I have odds it's hard for me to kind of conceptualize or understand. Well, I mean, I understand it, but it just doesn't seem as clear when the odd is less than 1. Because remember, the range on odds would go from 0 with the kind of the centering value there equal to 1 up to infinity. When we have an odds or an odds ratio of 1, it means that the two events are equally likely. And when things fall down in this area, which we've had right here, I think this is harder to understand. Now, if we look at the other way, if we look at 3.125 divided by 0.375, we get 8.33. This tells us that for being pro-life, the odds of a Republican being pro-life are 8.33 higher than a Democrat being pro-life. That to me just 8 times as much, 0.12 times as much. It seems easier to understand that. At least it does for me. I don't know. Maybe it's just me, but I've talked to a lot of people who feel the same way. Now, the reason I point this out to you there's actually quite a few reasons I point this out to you, because it's kind of cool. But I point this out to you because when we got our output from R, and you can see that we did this in the previous video, and I just typed it back in. When we came down here, we got Fisher's exact test for count data. And it said the sample estimate odds ratio is 0.12. Well, we just created that, and I hope now you have a better understanding of what that 0.12 stands for. And I'll show you something just a second. Just came to me. What if we did a different order? And it doesn't matter. But what I want you to also to focus on here is it says sample. And remember, when you take a sample and generalize to a larger population, we typically need to look at a confidence interval. So it gives you 3 forms. I always want you to concentrate on the true odds not equal to 1, not less than 1, or greater than 1, like the ones down there. Because again, guys, 1 is the center value. 1 is equally likely. When our odds ratio gets above 1, then it means that the event, whatever we have in the numerator, is more likely than the event in the denominator. When it's below 1, the event in the numerator is less likely than the event in the denominator. So what we got here is this 95% confidence interval. Notice it does not contain 1. And that says that this odds ratio is statistically significant. So as we found out back here with the Pearson Chi-Square, considering we had a very large sample size, we could use Pearson and not one of the others that allow for expected cell counts less than 5. We can see that there's a 0.95 probability that the odds that a Democrat is pro-life is between 0.086 and 0.166, that of a Republican being pro-life. Okay? Now, I want to point something out. I think you guys would probably figure this out, but I'm trying to not take chances on things. I think you would have figured out that back here, what if we had decided to do the calculations different? So what if we had decided to, for example, compare pro-choice to pro-life for Republicans to Democrats? Instead of what I did in this situation is I compared pro-life to pro-choice and Democrats to Republicans. But what if I wanted to focus on pro-choice across Republicans as it relates to Democrats? Well, we can see that we would have the odds of pro-choice for a Republican is going to be 80 over 250, which is 0.32. And the odds of pro-choice to a Democrat is 400 divided by 150, which is 2.67. And then, guys, if we take the ratio of 0.32 divided by the answer, we get, again, 0.12. Now, students are all the time, well, what do you want? You know, what's right, what's wrong? It just depends on what you're looking at. You know, it's just if I'm trying to make a statement back here, and I think that Democrats are going to be more likely to pro-choice than Republicans, then what I would do is I would start with Democrats, and I would look at the ratio from pro-choice to pro-life. I look at the odds. So it just depends on what you want to accomplish. All right, gang. Let's get out of politics and abortion, and that's a little bit too sensitive anyway. All right. And let's say that we've examined a couple of professors, and we want to see what's going on with their grades. So we have a Professor A and a Professor B. And this is C and higher. And this is D and lower. So we're going to pretend that we just have A, B, C's, and D's, and F's, and WDs are put in with D's and lower. We don't have any minuses and pluses, so we're going to go this route. So we pay attention one semester, and Professor A has 28 students, C or higher, and has 10 students, D or lower. Professor B had 48 students, and they had 114 with D or lower. Now, you might say, Dr. Darber, I don't need statistics. I can sit there and tell you that the percentage of students who had C's and higher were a lot higher in Professor A than Professor B, and I agree with you. But again, we're building foundation here for bigger, better stuff. So I want to run through this and get you guys thinking about some stuff, okay? Now, if I'm an education researcher, which I kind of like to think I know a little bit about that, I'm not going to do these calculations by hand. I'm going to use statistical software. So I'm going to get out of this, and I'm going to go to R, maybe. And I am going to do Prof A, and I'm going to do 2810, and I'm going to do Prof B, 48 114. I'm going to just do grades. Don't know what else to call it really. And I'm going to go C bind, Prof A, Prof B. Now, what I have to do next is I have to put the cross table command. I'm going to go all the way up to the top, and there's what I need. But this is for the pro-life, pro-choice. So I now need to come in and change that to grades. It's kind of a handy-dandy feature that R has. You can hit your up arrow. I think it works on Windows. I know it works on Mac, and go up and get previous commands. It's kind of like the second function entry command on your calculator. So you know, I can run this, and let's see what we get. Okay. The very first thing I'm going to look at is, yeah, I've kind of got the cart from the horse here. The very first thing I would look at is I would look at the appropriate null and alternative hypothesis. Okay, so I hope you know that by now that the null hypothesis that there's no association or relationship. I have no idea what happened to my P out here. That just was really ugly. Between profs and grades. There is an association. Relationship between professors and grades. Okay. So when we go to our R output, that's tough for a Kentuckian to say. We can see that first thing I want to look at are the expected cell counts, because I want to see if I need to be concerned with one of the assumptions. So notice that the expected cell counts are the second ones provided, or I can just go down at the very bottom and look at the minimum expected cell count and see that it's 14.44. So I have, clearly bigger than 5, so I have no concern with violating the assumption. The next thing I'd want to know is there any independence issues? And, that's extremely arguable here, that there could be. The next thing I'd want to look at is I'd want to look at the Pearson Chi-Square, since I've got a significantly large data set. I'm okay with using Pearson Chi-Square, and I have a value that's less than 0.001, so I have a statistically significant result telling me that there is an association between grades and professor. The next thing I'm going to do is I'm going to go up here and I'm going to look, if you look at the very last one, this is the standardized residual. So I want to focus on these values right here, and specifically I am looking for values that are higher than 1.96. I typically make it simple and just focus on 2, or anything lower than 2. So right here I see that the standardized residuals that are higher are for Professor A. So this is telling me that the observed students who received grades of C or higher was 3.6 standard errors higher than the expected. This tells me that the observed students who got a D or lower was 2.8 standard errors less than we would have expected. So, this kind of stuff would open up all sorts of discussion between people. Well, Professor A is a grade inflator and Professor B can't teach, and all that stuff. I don't know what's going on here. I just look at the data, and I can tell you that in this analysis that there's definitely a difference, and that difference is attributed to these two cells. The next thing I'd want to do is I'd want to come down and look at the Fisher's exact test for count data. This is 6.6. This is telling us that the odds Again, reading from left to right, the odds of a student getting a C or higher in Professor A's class is 6.6 times higher than the odds, or than the odds of getting a C or higher in Professor B's class. So for one reason or the other, and I don't get into that stuff. I'll tell you a story. Well, let me finish my stay. The odds are 6.6 higher of getting a C or higher in Professor A than in Professor B's class. Come down to the confidence interval. We can generalize from this data set to the entire population if Professor A and B were selected randomly, and if well, I guess we'd be focusing more on, we'd have to select a random class from all of Professor A's class in a random class from all of Professor B's class. So we would say that the odds of receiving a C or higher in Professor A's class at a 0.95 probability is 2.84 to 16.43 higher than it is to get a grade of C or higher in Professor B's class. All right, so guys, we know a little bit more than we did. So how would we write something like this up? Let's go back over to this, and what would I expect you to be able to say? I would let me get my computer set up. I'm trying to say something like there is a statistically significant relationship between grade and professor. And I would come in, we have a chi-square, degrees of freedom 1, 25.36. Let me check that. I jotted that down and earlier. Make sure I get that right. Yeah, 25.36. Okay, I thought so. Can't believe my dog doesn't want back in. That's just blowing my mind. And our p-value was extremely small, 0.001. Based on the odds ratio, the odds of receiving a C or higher in Prof A class is 6.58. The 95% confidence interval was going from 2.84 to 16.43 times higher. than in Professor B's class. And something to that effect. Okay. All right, gang. That's really all I got for this one. We're gonna get into some more stuff later that I think is actually really cool. But that's all I got. Take care.